Continuing with our work with parametric equations or parametric functions, let's talk about how we can use the definite integral with parametric equations to find length of a curve in a plane. So far we've used the definite integral to add infinitely many areas of rectangles, and that was to not just approximate, but to give us the exact area in the plane. We've also used the definite integral to add infinitely many volumes of cylinders so that we can get three-dimensional volume of a solid. And now we're going to use the definite integral to add infinitely many line segments. And this is how we're going to find the length of a curve in the plane. We have the length of this curve in the plane. Remember, just from good old algebra, we can find the distance between any 2 points in the plane. We'll call this the point x1, y1, and then we'll call this the point x2, y2. And we can find the straight line distance between those 2 points in the plane using the distance formula. And you learned this probably in Algebra 1, but maybe as late as Algebra 2, I'm not sure. So here's the distance formula. It's the square root of the difference in the x values of your 2 points squared plus the difference in the y values of your 2 points squared. And that will be the distance between the 2 points. So we're going to work on that prior knowledge, and we understand that what's happening here with this term is we are tracking the horizontal change that's happening, this horizontal change between x1 being here and x2 being here. That very first squared term is tracking the horizontal change, and this is tracking the vertical change. The y2 minus y1, or y minus y1, is tracking the vertical change that's happening between the 2 points in the plane. Now, we can talk about tracking change horizontally even if we have parametric functions, because we have some function in t that is the horizontal behavior that's happening for us in the plane. And then we have another parametric function that tracks the vertical behavior of whatever we're talking about, whether it's an object or whatever's happening in the plane. So even parametrically, we can still talk about horizontal change and vertical change. So instead of adding area to get the area in the plane, infinitely many rectangles, or instead of spinning this around some vertical or horizontal line and getting a three-dimensional solid, adding up discs or washers, now we're going to add up infinitely many line segments. If I wanted to approximate the length in the plane, I could just take some distances, several different points in the plane, and attach them by lines, and that would be a pretty good approximation of what's going on in the plane. So I could add up those finite number of line segments, and that would give me the approximate length in the plane. If I wanted the exact length in the plane, I would need infinitely many of those line segments. And that's where the definite integral comes in. So if we have two parametric functions, if we have f of t, that is the horizontal behavior of whatever we are modeling, and we have g of t, that is the vertical behavior of whatever we're modeling, based on the distance formula, hopefully you can see the distance formula right here, we're talking about horizontal change. And for us now in calculus, we know change is just the derivative. So we have horizontal change going on, and we have vertical change. So this is the same exact idea of x1 minus x2 and y1 minus y2. We're just doing it using calculus. So we're taking distance, the distance formula based on the distance between 2 points in the plane, and we're finding the length of line segments, but we're finding the length of infinitely many line segments starting at A and stopping at B, and A and B are, as you can see, t values. And f is a function in t, and g is a function in t. Now, this is just alternate notation, just Leibniz notation. These two things are identical, so whichever way it's given to you, you can plug it into this formula, and this will give us the exact length of a curve in the plane. Again, we're strictly in a geometric setting here. We're not going to have negative length. We don't have to worry about whether we're above or below the horizontal axis. We can still use this idea of infinitely many line segments even in Cartesian functions. If we have y given to us as a function of x, we can still track the horizontal change and track the vertical change, because the change in x with respect to x is always going to be 1. Now we have the distance formula that looks like 1, or 1 squared, which is 1, plus f prime of x. That's the change that's going on for our function in the plane, quantity squared, again, based on the distance formula. We're adding infinitely many of those line segments up, and we're integrating with respect to x. So we can even use this idea for explicit functions, non-parametric functions. You'll find that you're going to encounter the idea of length of a plane curve, length of a curve in the plane, much more often in a parametric setting than you are in the explicit function setting. But we could still do both. So let's work a few examples. The length of the path described by the parametric equations x equals cosine of t cubed and y equals sine of t cubed for t between 0 and pi over 2 is given by. So we don't even have to evaluate these definite integrals. Lots of times all we have to do is just set them up. So we know what we're looking for parametrically for length of a curve in a plane is we're looking for x prime of t squared plus y prime of t squared. We're going to integrate with respect to t, and those t values are straightforwardly given to us. And lots of times they are. Notice that that's really not going to help us here, because every single one of those definite integrals has the same interval of integration. So let's find x prime of t. That's the chain rule. Derivative of the outside, not changing the inside, times the derivative of what's inside. So there we are. This technically is part of the derivative of the outside, right? Y prime of t is the derivative of the outside, not changing the inside, times the derivative of what's inside. Now all we have to do is plug that into our formula. We want negative 3 sine of t cosine squared of t, and we want that quantity squared, plus positive 3 cosine of t sine squared of t, and we want that quantity squared. So we have 9 sine squared of t times cosine to the 4th of t plus 9 cosine squared of t sine to the 4th of t. Do we have anything like that here? 9 cosine to the 4th sine squared, 9 sine to the 4th cosine squared. So there it is right there. We don't even have to do any factoring out or cleaning up or anything like that. And usually in this context, the multiple choice questions are that straightforward. This is one concept that we count on to help us increase our BC score because it's really straightforward. No curveballs in this one. And lots of times they just outright give us our limits of integration. Now this says find the length of the curve y equals the sine of x from x equals 0 to x equals 3 pi over 2. Well, they give me my limits of integration. As I said, lots of times they do. Not every time, but lots of times they do. I am integrating with respect to x, so that is the form where it's 1 plus the quantity dy dx squared. And dy dx is the cosine of x. Now, this isn't multiple choice, so I'm going to need to do a little bit of work here to see if I can evaluate this definite integral. If this was 1 minus the cosine squared of x under that root sign, I could use the Pythagorean theorem identity and replace that with sine squared. But since it's plus, this pretty much tells me that this is going to be a calculator active problem. So you can pull your calculator out. This is just a definite integral. Your calculator's perfectly capable of evaluating that definite integral. So I'll let you do that. You can pause the video and I'll let you do that on your own. One last example. Find the length of the curve x equal the square root of the quantity t plus 1 and y equal t squared plus t from t equal 1 to t equal 5. So again, we're going to set this up. The integral from 1 to 5, square root of, we want dx dt, so that's chain rule, power down front, reduce the power by 1, and we want that quantity squared. We want dy dt, so that's going to look like that, quantity squared. This definitely looks like it's going to be a calculator active question as well. So I really don't think there's going to be anything that's going to ask you to do something that's going to be that time-consuming algebraically for such little calculus payoff. So again, practice putting this into your calculator because you definitely could be given a calculator active question that looks like this. And then, of course, you're just going to get your answer. Make sure that you are meticulous about entering this into your calculator and evaluating that definite integral. This is something that definitely can be done in function mode. Just put things in as if t was x. You don't necessarily have to be in polar mode to do this. This is free and easy points. Make sure you understand this is just based on the distance formula that we've known for many years now in our math work, and that we are using the derivative to find the horizontal change and the vertical change to plug into that distance formula, and the definite integral means that we are adding infinitely many line segments, and that's going to give us the exact length of any curve in the plane. So come to class next time. We'll work some homework problems.